today we've got a really good speaker, Rory Winston, who's going to talk about our packages. And so Rory's from Ireland originally, and he's looks like he might be calling Australia home now, so that's good for us. He's got a strong background, computer science, physics, London School of Business in finance, working in a Big Four bank at the moment. Whole lot of years of our experience, so yeah, it should be a great call. Thank you, Rory.
You build me up now, I feel like I'm actually doing something. Okay. Well, hi everybody, and thanks for coming along. Yeah, first of all, so Yuval and Shane have both got 2 new little babies, so it's basically our user group baby fest at the moment, and we've just found out ourselves, myself and my wife just found out a few days ago that we're going to be expecting another little kid, so we're going to raise a whole new generation of nerds with us. So my talk tonight is going to be on just building R packages. I've got 50 slides or so. I'm going to try and get through them reasonably quickly. I know that there's a mix of levels here. I mean, I'm sure there's probably some people here who probably know more about building packages than I do. And by the same token, I know some people have said here that they're beginners. So we'll try and find a happy medium somewhere. So without further ado, so this is going to be what I'm going to go through tonight. I'm just going to go through a basic example of building a package with some R code. I'm going to show you the bare minimum of things you need to build a package, and hopefully show you it's actually very easy. Show you why it's probably a good idea to build a package if you use code a lot. And the last bit I'm going to show you, I'm not sure how far we're going to get with it, but I'll show you just a very simple example of interfacing R to native code, in this case some C code. So if you've got any questions, if I say something you don't understand, or just raise your hand, feel free to interrupt and ask me. If you don't understand my accent, there's not a lot I can do about that, but I can try and speak more slowly. That's all right. I do have that problem occasionally. Anyway, so let's get started. So what are R packages? Well, R packages are probably the single most useful feature of R. So I was at one of the R user group conferences a couple of years ago, and one of the guys who is on the R core team put forth the idea that from now on, R might be something that the basic core of R stays relatively static, and any functionality, any extra functionality that people need around that will be provided by extra packages. So they're very important, they're taken very seriously. There's a lot of them. There's about, I think I counted almost like 3,000 between CRAN and a couple of other places. That's not necessarily, that's a good thing, but it also can be a bad thing. But they are very important and very useful. And the basic uses of packages are obviously to keep your code and data together, to automate various tasks that you might do on a regular basis. And one of the nicest things about packages is that you could package up. So if you produced a paper on something, you could package up your research, your code, and your data into a paper. And they're very much useful in the area of reproducible research. So, for instance, a lot of papers that you see on, say, Archive or one of those places, and you think, oh, that might be useful, it looks quite nice. It would be quite nice sometimes to be able to download a package that gives you, basically what the authors had gone through as well. So there are many reasons to create a package, and creating a package is very easy. R has got certain conventions. It likes you to do things a certain way, and if you do things a certain way, then it makes life very easy for you. So there's one little bit of pedantic things that you'll see sometimes people refer to, is that some people refer to packages as libraries, whereas a library is something different. A library is a collection of packages that lives on your computer somewhere. You can have multiple libraries, and a package is something that lives in that library, which is slightly confusing because the command you use to load a package is called library. But anyways. Okay, so this is the basic structure of a simple package. And like I said, R has got various conventions, so it expects to see things in a certain way. So we've got this description file, which I'll show you in a few minutes. You've got an R directory, which holds all your R code. A data directory, where you hold your data, obviously. And then we've got various directories which relate to sort of user help and examples that the user can run. we've got this directory which is related to internationalization. So R is obviously compiled for a whole bunch of different languages. If you run R on in a Chinese locale, you should see certain messages in Chinese, for instance. And if you create a package, you can also make some of your messages in that package localizable. And it's also, you can also put in, it's also got a placeholder where you can put some native code if you want to do that, and a directory where you can put tests. Now this is a subset of some of the directories you can have. This is maybe like a general subset, but as you'll see, we only need a couple of these to actually have a working package at a minimum. So if you want to see, when you load R, it installs a library of default packages onto your computer. And if you want to see what those packages are, if you want to see what packages are loaded up by default when you start R, you can use this get option command and use the default packages option. So I just use this on my vanilla R12, 212 or something. I started up, and it's loaded 6 packages by default. So the basic stats and utils package. So that's how you can see what's loaded up. If I want to see what packages are actually installed in my computer, in my default library, I can use this install packages command, which returns a matrix, and the matrix along the rows has packages, and the columns, so these are the rows, these are the packages that are installed in my local library, and the columns are various attributes of each package. So for instance, we've got things like the license, when it was built, the package name, other packages it depends on. I'll show you some of these fields when we actually create our own package. So that's how you get information about packages that are installed. And finally, to see what packages are currently loaded, not just by default, but what packages are currently loaded right now, you can use this packages command, and that shows you what's installed in, what's loaded up right now. There's actually a couple of different ways to get that, but that's probably the easiest. So that's just some basic overview about packages and their usefulness. So I was trying to think of a very simple example of a package that I could create. I thought, what's got some data and everyone knows about and I could possibly do? And then I thought, well, the lotto. So the lotto's got all the historical data online. This is a totally useless example, but fits the purpose. So basically, I thought, why not create a simple package that we can put our lotto data into, create maybe like a function and a couple of help files and so on, and just get a basic, simple working package. So without further ado, this is my Oz Lotto package, which I'm going to create using this command, this package skeleton command. Some of you would have used this quite frequently. But this package skeleton command is R's convenient method of creating a package. I could build up a package from scratch. I could create all the directories, put everything in the right place, but R allows me to create one very easily using this package, and I'll show you how. So the first thing, I'm going to download some data that we're going to use in the package. So this is just I just went out to the shell and I used this curl utility, which is a Unix utility to, well, it's a utility to allow me to do web requests. So I downloaded a zip file from the Tattersalls website, which has got historical data in it, and I just unzipped it. So this is going to be the basis of our data file. And then using the read table command, which I'm sure some of you are familiar with, I load in the file that I've just unzipped. It's a CSV file, so I'll just specify that. I give the columns some names, so the draw number, the date, the various draws of the bowls from 1 to 6, and some draws seem like they have 2 extra numbers or bonus numbers, but not all of the draws have these bonus numbers, and where they don't, they designate that with a dash. So I've just said whenever you see a dash in the code, that's going to be NA, which means it's not present, and it returns, so that basically is a data frame. And in the data frame then, one of the fields here is a date, so I just turn this into a proper date using the stir ptime command, which basically just takes in a string and I tell it what format the date is in, and it turns it into a proper date object, so I can do some date calculations with it. And so if I look at the first 4 rows of this data frame. I can see I've got draw number, date, the first 6 numbers drawn, and then these are the bonus numbers drawn. And as you can see, not all of the draws have a second bonus number. So that's it. Pretty simple. And one final thing I did was that by default, I told it to rename these columns from 1 to 6, but R has got some logic which is built into one of the functions it uses for trying to put names on your columns, where it doesn't like doing that by default, and it puts an X in front of them. So if you see on this frame, even though I said name these columns 1 to 6, it prefixed them with an X. So I'm just going to override that here and say change the column names for this subset of the data frame just to be draw 1 to 6, and that's all that's doing. And so this draws object is just a separate object which just contains the first 6 balls drawn. So that's all my data. So that's it. I just have 2 pieces of data. I've got a lotto object and I've got a draws object. And now I want to create a dummy function to put in the package. So I'm going to create a function that just does a bar plot of the number of frequencies for the total of the draws. And this is a really simple function that just says, when I get in this object X, do a bar plot, unlist the object, which basically means take all the objects, rows and columns, and unlist them into a single long vector, and just set some colors and change the orientation of the labels, and just produce a graph. So it's basically a very, very simple bar plot. But this is our function. So now I've got some data, and I've got some code, and now I'm going to try and put these into a package so I can reuse this again. So before I create my package, I want to see what I've got that I can put into my package. So this function is just something I ran in my workspace to just show me what objects are in my workspace, and for each object, print out the class, the type of that object basically. So this shows me I've got 2 data frames, one called draws, one called lotto, and I've got one function called plot frequencies. And this is going to be the basis of the package. The next thing I do is this package skeleton command that I told you about earlier on, I just run this command, and what this invocation is saying is it's saying, run the package skeleton command, create a package called lotto, and the contents of this package is going to be everything that's in my workspace. And that's what this is. So this ls command lists everything in my workspace, and the package skeleton command will take all of those objects, put them in the right places in the package. And so it tells me, for each point, it tells me what it's doing. So it's creating the proper directories, creating this description file, creates a readme file, which gives you some pointers on what to do next, and then it's finished. So that's the package created. And what it creates on the disk, if you go out to your disk and actually look at what it's just created, it looks something like this. So it's the package name. Underneath here there is a data directory. And this is the name of the 2 pieces of data I had in my workspace. It's created these RDA files. And then it's created this man directory, and it's put in some, I'll show you these in a second, but these are actually help files for each object it's found. And then for the function, it only found a single function in my workspace, and for that function it's created an R file, which has got the code for that function in there. And then a description file, and just a readme file. So there's basically 3 sections. There's data, there's code, and there's help. And that's a very simple, sort of basic, minimal package. So this package won't work by default. This is not something you can actually.
Question.
Yeah.
So is this always like under the data directory is always extension RDA, and under main is always RD?
Yes. Yeah, by default. I'm going to go through all of the different sections in a second and show you exactly what's in each one and what's in each bit. So But yeah, that's basically it. They're just different types of file. So I think I'm going to show you the data.
If I create, say in my workspace, if I created a temporary variable somewhere, where would it fit? Like your example is nice. Everything is exactly what you want.
Oh, if you have got a workspace and it's full of lots of different objects, and you want to create a package, but you only want to create it from a subset of some of the objects in there, then what you do is, when you run this package skeleton command, instead of saying list equals everything, you would just pass this a list of a vector of names. And so for each object you want to put into the package, you can say exactly which ones you want to put in here. So because I'm starting from scratch, I can just do it the easy way. All right, so the first file I'm going to show you, the first bit of the project I'm going to show you is this description file, which is probably the single most important file in the package, because it tells R all about what the package does and what's in it. It's in this special format called DCF, or Debian Control File, which comes from the Debian Linux operating system. There's lots of different fields you can put in here. And some of the fields in here can have different values, like ranges between A and B and X and Y, and I'll show you exactly what that means. So here's my Lotto package description. This is the description file. I've just put in some very simple values in here. And this is sort of a minimal set of information. So I think every field in here is actually mandatory, and you can't actually get away with any less than this for a description file. So what's the package name? It's a package, obviously. There are different types of package object we can have. The title, version, author and maintainer, things like that. And this is the kind of interesting stuff. So when you say depends, it means in order for this package to run, in order for this package to load correctly, I need everything that's on this line. So, and one of the basic things you can say is, you can say, what version of R does this package depend on? So if you write something that works in R 2.12, like you depend on some functionality that was introduced in 2.12, so it won't work in any other version, then you've got to specify, well, you should specify that you depend on a specific version of R. And I think a lot of packages do this. So you'll see a lot of the basic packages you get with R, they will normally depend on some functionality that was introduced at a particular version, and so they'll say that. There's also a license field, which is where you specify what license that your package is released under. So most of the R stuff is released as GPL, but you're free to put in, any sort of open source license that's supported. And the final field, which is also mandatory, is the lazy load field, which I'll tell you about in a minute.
Rory, just on the depends one, nothing you've got there would actually depend on 2.4. It's just that you happen to have it.
Oh, I just put it in there just for illustration. Yeah, so there's nothing in my package that depends on 2.12. Like the package is so simple that it would probably work on or 1.0, but a lot of packages do have certain requirements. Actually, I think I've got a better example of that depends line here, actually. So this is the depends line is obviously for if you depend on a certain version of R, or alternatively, if you depend on functionality that's in other packages. So this is an example from there's a package called Highlight, which is it basically allows you to, inside presentations like this, it allows you to embed R code and have it very nicely syntax highlighted, so it's colored up very nicely. Anyways, it's a very nice little package, and the depends line for this was it's probably one of the most busiest ones I could find, but it's basically saying, I need this version of R, at least 2.11, and I also need 4 other packages, and this particular package, the parser package, must be at least that version. So that's the kind of thing that you can specify if you need that kind of flexibility. So that's the description file. So that's a basic description file, and that's enough to get it to work. The next thing was when you were asking about data files, the data directory with the RDA files. So RDA is a special format. Like if you've got a CSV file stored in your workspace, it's not going to just save the CSV file to disk, because that's obviously quite inefficient. And there are also issues with, if you've got an R data file and you give it to somebody else with a completely different OS architecture, they may not be able to load it in properly, depending on how it's represented on disk, if it's binary data or whatever. So R uses this sort of platform-independent format to store all of its data files in, and it's called an RDA or RData format. And if you actually go out to the shell, if you go out to the operating system and look at one of these files, these RDA files, they're basically just a zip file. And inside the zip file is all your data stored in a specific format. And it just means that no matter what OS or somebody else is using, you can always give them this data and they can always load it. And actually one thing I forgot to mention is that you could generate an RDA file yourself by just using the save function. So the save function, you can specify a piece of data and you could just say save it out to that file name, and it will generate exactly the same format. Okay, so that's the data directory. There's not a lot in the data directory, it's just taken our data and dumped it in there. The third section was the help section. And the help section contains a whole bunch of these RD files. So RD files is like it's kind of like, if anyone's here has used LaTeX, it's very, very similar to LaTeX. It's basically a markup language where you can write your help files, and then they can be compiled into sort of a number of different formats. So if you're using R on Windows, you can type help and you get a HTML browser. If you're using R at the console, you get a console help file. You can also have PDF help files, but they're all generated from the same source. So it uses a markup language that's very similar to LaTeX, if you've ever used that. And I'll show you an example of an RD file. So this RD file here is, let me just go back and show you where this is in the package. This is what I put in for the RD file here. And this is the documentation or the help for this function. So you can see there's various sections, but I'll just go through the basic structure of it. So we've got the title of the function, and you've got this alias command, which means that in R, sometimes when you type help for a certain command, you get directed to a page that's got help for a whole bunch of commands in there. So you can alias a lot of commands to one single help file if you want to do that. And there's the title. So the various sections are the description of the function, some usage, so you can put in some examples here of how the user could use this function, references to other functions, and at the end there's some examples. So you can actually put in some example code that the user could run, and when the user types example plot frequencies at the prompt, it will run whatever's in here. So that's a very simple help file. I won't go through all of it, but that's basic. That's basically it. It's quite simple. And I think you also saw that it also generates help files for data, not just functions, but for data. So what R does is it will look at your data, it will look at every field in your data and all the data types, and it will generate skeleton documentation for the data. So for instance, I had a data frame called, I think it was Lotto, and it had things like a draw number, a date, 6 numbers, and then 2 supplementary numbers. And R has inspected my object and generated sort of skeleton documentation for each field and given me the type if I wanted to go to that level of detail in documenting it. And it's probably a good idea, I guess, if you're going to be supplying users with data to document it. So that's the RD format for data and functions. And as you know, so when you use help in R, you've got PDFs that look like this. This is what gets generated from the RD files. So here's all the contents of the description on the front page. If you ever look at a package on CRAN, you'll see this. You'll normally click on this to see what's in the package.
Did you say that this is automatically generated once you produce the package?
It's exactly, it is. So well, this isn't automatically generated once you create the package, but the next step I'm going to show you is there's a single step which will do all of this for you. So that is a package, and it's also got some quite very neat features. It's kind of smart about certain things. So for instance, you can put some mathematical markup into your help files, and when they're generated in PDF format, they'll use the very nice LaTeX representation, so all your equations look nice and all that kind of stuff. But if you look at the help from the console, you'll see that it reverts to a simplified markup. So it's kind of smart enough to be able to figure out, for each environment, how to handle things like that. So that's the same snippet from the PDF, and that's the same snippet from looking at the help in the console. And it's all generated from the same bit of text. Okay. So all right. So that's everything. So that's all we need to create the package, and we've all the skeleton bits.
Do you know when it outputs the HTML version, how it deals with these equations?
So I think by default it actually reverts to this simplified thing, but it doesn't do it as far as I know. But it would be nice if it generated some math ML or something, some kind of markup. But I don't think there's any support for that at the moment. At least not in the base package.
I think there was some discussion on one of the main lists about including some JavaScript package that would do this.
Yeah.
The trouble is that it involves downloading a 130 megabyte file or something. So.
All right, fair enough. Yeah, probably not a good idea.
Not going to happen.
Yeah. In fact, because I was actually looking at this stuff recently, but it might be the same package, but there is a JavaScript package out there which actually generates it all in the browser, but generates amazing looking equations, but it does it all in the browser. Normally what people do, if you see web pages with sort of nice maths, basically what they've gone to LaTeX on the server, they've created a graphic and brought it back into the browser, and that's how you get really good looking equations. But that's probably the same package you're talking about. Probably not practical for this kind of thing. So okay, so that's enough talking about the structure of the package and what's in it, because there's not much more than that really. So now let's actually create the package so we can load it and use it. And to do this, you've got to go out to the command line, and you've got to have R in your path, so when you run something, R is available. And this command, R command check, is basically what you run to QA your package, to make sure it's ready to load and everything. And when you run R from the command line, it's got a whole bunch of different commands and different things you can do, and they all start with this R command something. So basically what you do is we'll go to the directory where the Lotto package is, and we'll just say R command check Lotto. And then what it does is it runs a whole series of tests in your package, does a whole QA on it, makes sure you've got things in the right place, looks at your description file, makes sure you've got all the mandatory bits in it, and it tries to ensure that when it passes, that you've got a sensible package that somebody else can pick up and work with. And there are lots and lots of different tests in there. So the basic, what you'll probably end up doing, and what I end up doing quite a lot, is that you'll never get it right the first time, you'll end up having to iterate. So you run the command check on your package, it'll generate a directory with some errors, if there's any, or some output, look at the errors, fix it up, and then back to step one, and keep going around this loop until you've actually got a package that passes. And once you've got a package that passes, then you can actually load in the package, the generated package. It creates a directory with a generated package in it. It can be loaded into R, and you can use the library command to load it in, just like a normal package. Now what I'm doing in this case is, I haven't actually generated the package properly. I've just run a check command on it, and it's sitting there on my disk. It's not in a zip file or something where I can just hand it off to somebody or upload it to a repository. So when I use the library command to load it in, I've got to sort of qualify slightly and say the library that I'm looking at is just on my local disk in this directory. So, but basically, this will load in the package as normal, and you've got a working package in there. So if that all looks good, if you're happy with that, then the next step is to generate something which can be given to somebody else or which can be passed around and shared like a normal package, loaded into people's libraries. So the next command you run is this one called R command build. And this will generate a binary package. On Windows, it will generate a zip, or on Unix, it will generate a tar.gz file. So when you see, when you're on CRAN and you see the packages, and normally they've got a few different download options, they've got a tar and a zip. So they've just run this build on different platforms and then they've collected up the results and made them available in one place. There's also the binary option, which means that we're just generating a binary package. There's not going to be any source code in this package. It's just going to be an optimized binary package. So, and once we've got that done, then we can install the package into our local library. So this is installing the package from the disk. So I'm saying, here's the file name of the package that was just created, and this is the type of file name that R will generate, and it loads it into the library. So I think normally when you do, how many people install packages using this command line format, or how many people use it from the GUI? So you click on the GUI and it goes, you've got a repository and you click through the packages. Do most people do it like that, or do you do it from the command line?
No.
You do, yeah. I always find that the command line a bit easier to work with that kind of stuff. The GUI sometimes I find a little bit flaky, but it doesn't matter. This is exactly what you're doing. It's the same thing.
So do you need to have permission, like a privileged user, to install these? Where does that package going to live? Together with
There's no real concept of that. If you've got permission to read from here and write into whatever the default library is, then you can install the package.
By default, all packages just basically unzips or uncompresses a file and puts the contents into the library folder under your R installation. So you need write access to that folder by default.
Exactly right, yeah.
Install to a different folder if you want.
yeah.
It's
Because I don't have permission to that.
Oh, okay.
Like we have security divisions,
Yeah,
then you're not allowed to go there.
It's on Linux,
You're
there's
doing
a
the
file directory.
Huh?
If you're on Linux, you've got a .r directory, I think it's called, and it gets put in there.
It's a problem when we are behind a firewall. Now, basically, you will not be able to connect to the repository. I think the R help file has a solution for that.
Yeah.
I faced it, and that I don't remember the command now.
Are you using Windows?
Yeah.
Yeah, there's an option you can specify to get it to go
Yes,
through a
to-
proxy.
yeah.
Yeah, because I had that problem before, but there is actually a solution for it. And in fact, if you install R using the Windows installer and you click through all the steps, I think they added in a step a while back where you can actually click that option. There's a little checkbox that says use this option, and so it's turned on by default. So you should be able to go through proxies and that kind of thing
I
if you're
had
set up.
something in command line that was an option.
There is, it's on the command line as well. But yeah, but you should be able to, as long as you've got permission to be able to, I mean, you can have a library wherever you want. So if you've got permission to write here but not to here, you can specify that your library lives over here and install all your packages into there. So it's pretty.
So I can always just manually unzip and untie and put it wherever I want it.
Well, yeah, or you tell this command where your library lives. Is the easiest thing. So there's other options to this command too. So you can say my library lives over here, and then your package gets installed over here. And once it's installed, then you just load it as normal, just by saying library, whatever. So that is our package built and loaded. Okay, so that's it for package, simple package. But there's a couple of things that I didn't go over. There's some more advanced stuff that kind of tends to trip up people sometimes, including myself when I first came across it. I'll just go through it briefly. One thing is namespaces. So R's got the concept of namespaces, and what this means is that when I create a package, so say if I create a package and I've got a function called mean, well obviously when I load that package into R's already got a function called mean. So when somebody types mean something, what is it called? So the way R gets around this is you can encapsulate your functions in a namespace. So I could call, my package is called Lotto. So if I created a namespace for my package, I haven't done it here, but if I created a namespace, I could put all of my functions under that namespace. So instead of, so when somebody, if I had a function called mean, and somebody wanted to refer to my function mean and not the built-in one, they could say Lotto : mean. And so basically it's a way of separating your functions from other packages' functions. And it also allows you to keep some functions private if you don't want users to necessarily play with them, or you think they should be internal for some reason, then it allows you to do that. So you'll see, I mean, quite a lot of packages use this, but for a simple package there's really very little need. Lazy loading is another thing. So if you remember, the one thing I skipped over in that description file was this lazy load item right at the very end. Now this is something that was introduced a long time ago now into R, but this is the default behavior for all packages. And what it means is that, how best to describe it, but what it means is that when you look at a piece of data or a function in R that you load from a package, what you actually get is, it doesn't actually load that function into the workspace. It doesn't actually load that piece of data into the workspace until you use it. So if I, for instance, look at this, does anyone familiar with the air passengers data set? Right, so this is a default, one of the built-in data sets that comes with R. It's like an interesting piece of data. And if I look at this data set, and I just say to R, I say dump this data set, so give me the basic internal representation of this data set, how you look at it, and not how I look at it. So I say don't evaluate it, just give me the raw output of this data set. It actually comes back with this function, lazy load, db fetch, etc., etc. And it's got this thing called a promise. But what this basically is, this is sort of more esoteric stuff, but whenever when this air passengers data set is first accessed, what R does is R goes out to the disk, and it's got an index of data sets and functions in that package, and it loads in a sort of an optimized version of that data set from disk. So even though you think you've loaded up like lots of packages, R doesn't really load them up. It just loads up an index to those packages and tells R where it can find them. It's like a set of pointers. And then when you actually access these functions and data sets for the first time, it transparently just loads them for you behind the scenes. And the reason it does this is if you've got, well, there's a couple of reasons. One is memory use and the other one is speed. So if you've got an R installation with like lots of packages, this makes the startup time a lot quicker, and it also makes the default memory usage of R a lot smaller. So it's something that you might see here and there. You may not see it just as a general consumer of packages, but if you write packages, then it's probably something you need to be aware of what's actually going on, because when you look at your generated package, you're not going to see your actual code, you're going to see something else that allows R to do this. Yeah, so that's just a bit more of esoteric stuff. Also, if you're a developer and you're stepping through R code, you'll find that it's always skipping out to this lazy load thing, which is incredibly confusing the first time you come across it, but once you figure out what it's actually doing, it kind of makes a bit more sense. So that is that. All right, so the last section I have was just a reasonably simple example of interfacing R to native code, which is one of the neat things you can do with packages. So the reasons why you might do this, and there's quite a lot of packages in CRAN that do this. I've done this, so say at work I've done this a couple of times for interfacing to, say, systems that provide data, that there's no other way to access the data except via, say, a C++ interface or something like that, but I really want to be able to get the data conveniently in R, so I write a package that's like a wrapper around this C++ API, and then I can just access the data sort of transparently and easily. Other reasons why people do this kind of stuff is that sometimes R is just too slow. I mean, R is quite slow for a lot of stuff. Internally, it does a lot of things, copies data and all that kind of stuff, which means that if you do lots of large calculations with lots of data, occasionally it can be quite slow. And one of the ways that people get around that is that they skip out to native code like C++, and they do a lot of the heavy-duty calculations in there. And there are also some more interesting things you can do by going out to native code, and people like to work around some limitations. So R is a limitation on the amount of data you can store in memory. It's got a limitation on the number of rows you can have in a data frame, for instance. And what a couple of people have done is they've written packages that basically treat the disk as memory. And you can't do that kind of stuff from R. You have to write it in native code and allow like a nice convenient interface to that from R. So there are many reasons why people do this kind of stuff. And I'm going to show you like a very simple, contrived example. But the first thing is just a bit of a warning that the learning curve with R is quite steep for beginners, as it is. But when you begin to look at R and native code together and how R works, it's a whole another level completely. And the reason for that is some of it's historical, and some of it's just the sheer size of complexity of what goes on in R. But R is a very eccentric programming language. It's extremely quirky. It's got its roots in functional programming, and the guys who created it originally really wanted it to be something else. They were looking at Lisp, and they really wanted to write a stats package in Lisp. And if you look at the C code in R, this is a line of code from the internals of R. You've got all of these things in here, which if somebody was a Lisp programmer, they would look at that and go like, oh yeah, I can see what's going on there. That's pretty straightforward. But this is actually C code, which is slightly confusing. Also, this kind of code here is something that looks like a completely different language, but this is actually a valid R command that you could type in at the prompt, and it will give you a result. It will interpret this and give you a result. And this is equivalent to this. So this is just the sum of squares plus the square of the sum from 1 to 10. But here is one way we can put it in, which is a very Lispy kind of way, if you've ever seen Lisp. And here's how R does it. And the thing is, the reason I'm bringing this up is if you do any kind of work with the R internals or C code or whatever, or try to write a package that integrates with C code, you'll come across this kind of stuff, and initially it's very confusing. And the last thing is that another thing that catches a lot of people up, even people on the R core team, occasionally there's always bugs reported against this kind of stuff, is the garbage collection. So it's not something you really would notice a lot, but in the background R has got a garbage collector which runs and tries to pick up data that you're not using anymore. And it just, you wouldn't even know it's running, it's just transparent. It saves you from having to explicitly throw stuff out of your workspace. But where you do need to be aware of it is when you actually start writing native code, because in that case, you need to manage all of your stuff so the garbage collector doesn't swipe it away from you while you're using it, basically. It's a common problem with C and C++ programs, but it's slightly more pointed with R. And like I said, this kind of stuff trips up even the really experienced guys. So with that in mind, I'll just show you a very simple example of something that I knocked up. Like I said, a very contrived example. And I was trying to think of something like a very quick and simple example. But one thing I was thinking of is that in R, when you work with a matrix, I don't know if you know this, but if you use the power operator on a matrix in R, you don't get that matrix multiplied by itself. So if you say x squared, where x is a matrix in R, you don't get the matrix power operator, you get a scalar power operator. So if this is your matrix and you say matrix to the power of n, you'll just get the scalar element-wise power of the matrix. And that's how it's documented work, and that's how it does work. So that's fine. But I thought, well, wouldn't it be nice if we were able to add some kind of operator here that when we did, say, x squared, where x is a matrix, we were able to get x multiplied by itself, i.e. a proper matrix multiplication. And that's quite easy to do. So the operators that I showed you here, for instance, the squaring operator and the matrix multiplication operator, they're just functions, and they just take two arguments. So they take what's on the left and the right hand side as an argument. So I'm just going to create a new function, and I'm going to put these two percentage signs around it to make sure to align with the rest of the matrix functions. And I'm going to say it's a matrix squaring function. And this is my function. And when I pass this, when I use this function, is going to raise this parameter to this power using matrix exponentiation. So I'll just go through it very quickly. So the first thing it does is it checks that the first argument is a matrix, and if it's not, it'll throw an error. Then it gets the second argument and tries to turn that to an integer, because we want an integer power. And then it does some things like if you've got something to the power of 0, it just returns an identity matrix. If it's 1, it just returns the matrix back to you again, doesn't do anything. And then this little loop here just keeps going until we've reached our desired power, and then keeps multiplying the matrix by itself. So that's very simple. And once we've defined that function, if you see here, this is how we've defined the operator. So I'm just saying this operator is a function that takes two things, and because I've prefixed it with these what's the word? What are they called? Back quotes. Because I've enclosed it in these back quotes. I couldn't make it up. So that means that OR actually treats it like a special function. If I left out the back quotes, OR would try and evaluate it like an operator, and it wouldn't work. So anyway, so I can try the function. I just typed it in, and now I can try it by saying x matrix power 2, and it returns back x multiplied by itself by matrix multiplication. So that's tremendously exciting. So what I'm going to do now is now I've gotten to that point, I'm going to say, well, this is actually a little bit slow, because every time I do this in R, it's going to do a copy, it's going to do X, Y, and Z, and if I use this function with a particularly large power, it's probably going to be quite slow, and potentially use up quite a lot of memory too. So the general solution in these cases is to go out to native code and do all our calculations in native code. So I'm going to create a new package for this, as distinct from the Lotto package. I'm just going to use this package to demonstrate the native code. And this package will only contain two things, basically. It's going to contain a native code, a C file, which contains all my calculations, and it's going to contain, that's going to contain a function, and it's going to contain a simple R file, which I'll show you, which is just a bridge between C and R. So, how many people here know C? Oh, cool, all right. That's actually that's quite good. Quite impressed. All right, well, let's have a quick look at this then. So I'm just going to step through a couple of slides, which is the actual code for this function. Now, I don't expect you to understand any of this, because a lot of this is very R-centric stuff, but I'll just tell you what's going on at each point. So this is my function, and you remember I had my other function took in one argument, which is a matrix, and one argument, which was integer power. So this works exactly the same way, and I'm going to call it in the same way. So I'm going to say, I'm going to return something, and I'm going to take in two arguments. And as you can see, I'm using this generic R type here. And I just do, first thing I do a couple of checks. I get the dimensions of the matrix, and I make sure that it's a square matrix, fine. And I make sure that the power that I've passed in is a valid number, fine. And then I was trying to be a bit clever here, and I just say, well, if the exponent is -1, then I'll just invert the matrix and return that. And that's just I've got some R magic in here that does something anyways that's irrelevant to the point at hand. And then the real sort of work is here. And basically what this loop is doing in the C code is I'm just saying, create an identity matrix, and if the power is 0, return that. Otherwise, go around in a loop and keep multiplying the matrix by itself until until I've basically multiplied it n number of times. And then at the end, I return the matrix. So that's it. That's.
So can I just understand the performance implications here? So Okay, so that SX thing is obviously some kind of a pointer to an
It's an
IR
R,
script or
yeah,
whatever.
yeah.
And then here this real macro is then saying, let's assume that that's kind of treat that as a array of
Yeah,
nulls or whatever.
exactly,
So
yeah.
in terms of the code this is generating, it's going to look pretty much like a direct array lookup. It'll be pretty fast. Or?
That's exactly it. So the difference between it, so the internal R matrix multiply stuff looks a lot like this, but the difference between doing it here and doing it in R is that doing it here, we basically copy it once, and we've got our matrix here, and which is like a vector of numbers, and then we just do all our calculations using this vector directly. But if we go back to the R function that I created earlier on, well, every time it goes around this loop, right, it may do a copy. So there's going to be lots and lots of copies in here, and that's what makes R slow. So that's the reason R is, people complain about R being slow, is that it does lots of copies of data, and you don't do that in native code. You just get your data, and then you get to work on it, and that's it.
And presumably the matrix will just be stored in column order or something.
Yes, it is. Yeah, I think it's in column major order by default. So yeah, but anyways, yeah. I mean, I don't want to get too caught up in the details of it, but that's just something that we have in native code that we can call into, and it's all in one file. It's a C file, and if I want to turn this into something that can be loaded and used, there's this other command called R command shlib, which is short for shared library. And once I've created this file, I can just run R command shared lib on the C file, and it'll generate, on Windows it'll generate a DLL, and on Unix it'll generate a .so. And these are just dynamic libraries which can be linked in and loaded. And the second last thing to get this to work is I need some way of relating what I do here to what I type at the R console. So I need some way of being able to invoke that function from R. And some of you may have seen this kind of thing mentioned before, but there's a feature in R called .call, which allows you to call out to native code directly from your workspace. So if you've got a function defined that's loaded into your workspace and R knows about it, I could just call it by passing its name and passing it some arguments. And R does all the work of converting arguments to the right format and so on. So I'll just go quickly. So the very last step, there is one more step to get this kind of stuff to work, and that's, we've created a shared library. Now we want the shared library to be automatically available when we load our package. And if you remember I said R is an eccentric, sort of a quirky language, well, it is that the default way of getting this kind of stuff to work is you create a file called zzz.r, and in this zzz.r, I have no idea what it's called that, you put a function, and this function has to be called first lib, and if you do this, this function will be invoked whenever your library is loaded. And people normally use this kind of thing as a hook, so to load in your shared library, using a function to load a shared library in when your package is first loaded. So if somebody's at the prompt and they type in library matrix exponential or whatever it is, then because I've defined this hook function, it'll load in the DLL or load in the shared library, and then everything's available. So with that,
would you normally have a bunch of functions in the one library, or a separate library for each function, or how do we normally do that?
I'd say you probably, well, it depends what you're doing, but I mean, if you look at the functions that are out there,
I mean, this library.9 everything could be loading a bunch of functions.
you can load a bunch. Yeah, you can load a bunch of DLLs. But to be honest, most of the time when people use this kind of native code stuff in R, it's normally pretty small. Like they normally do it for one or two specific things. It's normally, there are only a few packages I've seen that have like lots of data code in there. Because the whole idea is to write as much as you can in R, and this stuff is only for if you really need it. Just to show you this package, this is the package structure for this example. So I have virtually nothing in this package. I've got a description. I took all the help out because I couldn't be bothered. And then I've got a C file, which has got that function I just showed you in there. And I've got that magic zzz.r file, which makes sure everything's loaded. And if I want to use that package, I first install it as normal. And then It says package matrix successfully unpacked. And then I say, I load it in. And because I've defined my zzz.r file and I've told it to load in the library, when I execute this, in the background, my shared library gets loaded in, and all my native code functions are now available. And then I just redefine the function that I defined earlier. Instead of being an OR this time, I'm just saying call out to native code and just pass the arguments out. And then when I invoke it, I just get exactly the same result, but all the work has been done in native code. So presumably, if I didn't have time to do any measurements or whatever, but if I did the first function for an extremely large power, it would be quite slow. If I did it for this function, it would be less slow. I can't tell you how much. I know that's pretty bad, but I didn't have time. I'm sorry. But I have done this before. I did this before for something else, and it was something very similar. Actually, it was like a matrix. Some matrix calculation, and the difference can be dramatic, right? If you're working with sort of a lot of data and a lot of calculations, because, like I said, every time OR copies something, you pay a performance cost. So, I mean, that's the reason why, for a lot of internal OR stuff, it goes out to some, BLAST library and does everything under there. So that's why this kind of stuff is good. So that's it. That's a very simple example of native code. I know a lot of it seems like there is a steep learning curve there, and a lot of it is quite awkward. But if you are interested in doing this kind of stuff, and you do know some maybe C++ or C, then there is an easier way. There is a better way, and this is the way I would probably go for any of this kind of stuff if I was going to do it now. There's an RCPP package, which is maintained by a couple of guys, Dirk and Roman, and they're both very smart guys, and they've done a fantastic job with this package. And what they've done is they've taken a lot of the messy stuff I was showing you, and a lot of the quirky OR idioms and things like dealing with the garbage collector, and they've all packaged it up very nicely. They've made it very easy to use, and they've packaged it up in a way that it uses what I call like modern C++. So the kind of C++ code you see out there can vary greatly in its understandability and quality, but they use all the best features of modern C++. It's very nice, and you can create integration to other packages very easily. So I'd recommend you have a look at that if you're ever interested in, or you ever need to do this kind of stuff. Finally, so somebody was asking about Windows, and I've done quite a bit of more stuff on Windows as well. All this stuff is normally just as easy to do on Windows as it is on Unix, provided you install all the prerequisites. So I've created extensions in Visual Studio, I've created them in whatever, it's normally not a problem. But like I said, there's a couple of guys, one of the guys who works in the OR core team, he maintains some software that if you use Windows and you want to do this kind of stuff, you should really download, because it'll make your life a lot easier.
Just a question on that front. When you do something like R command SHD with Visual Studio, do you actually have to make any tweaks, or can you just run it straight like that? Because I think the last time I tried this was probably a few years ago now, but I needed to download MinGW. It wouldn't work with the Visual Studio I had at that time.
Yeah. So in this tool set that you can download from here, MinGW is in there. But if you want to use the Visual C++ command line compiler, you can do that as well.
Okay.
But sometimes you do need to add some tweaks. Like sometimes you need to, like you normally need to specify the command line yourself, and sometimes you need to add a definition file to tell it what's in the DLL. So you can do it, but sometimes it does take a little bit more tweaking. Like OR assumes by default, the default starting position for OR is that you're using Unix, and anything else, if you want to do the more advanced stuff, sometimes it's a bit more work. But it's getting better. It's definitely getting better at that. So I guess, like I said, a lot of you probably know some of this stuff already, and you've created your own packages and so on, but some further references, or look at just go to the command line, type or cmd, and from the list of commands, you can type, they've all got help, so take a look at that. Or documentation, which is quite copious. Sometimes it's not so easy to get around, but it's quite good. The mailing lists are obviously great, but I also like this guy Pat Burns, who has his website burnstat.com. He's very active on the mailing list, but he's written quite a lot of documentation around various things to do with R, and he's great, very understandable and very interesting. So that's it.
But to upload to Grand
Oh.
website is not anyone can do it.
Well, yeah, anyone can put the packages in the right place. There is a publicly available place where you can put packages onto CRAN, but well, the first thing I'd say about uploading to CRAN is think if you really need to upload to CRAN, because there's already 3,000 packages up there, and if you've got that's the one thing I find quite confusing about R sometimes. I sometimes find it really hard to figure out what package to use, because there's normally, for one particular thing, there'll be like a whole bunch of packages and they kind of overlap, and they don't do quite the same thing. But it's available to anybody to upload to CRAN, but it's not guaranteed that you'll get it published there. Somebody has to look at it, and it's got to be set up to build and all that kind of stuff. So I don't think you'll be seeing the Oz Lotto package up there anytime soon, for instance. But yeah, it's relatively easy, and if you want to find out the exact procedure, there's a guide, the R extensions guide, it's in there.
I've noticed that a lot of native code with R seems to be written in Fortran. Do you get the impression that it might be easier to use Fortran than C for this, or is it just maybe a historical accident?
No, I think it's just history. I think the R used the linear algebra libraries that it uses. A lot of them are Fortran based. And the what's the name of it? Netlib, is it, or whatever?
Yeah,
Netlib, yeah. But I think I think it would just be so much work to have to port that stuff over.
Because Fortran kind of deals with vector operations and stuff so painlessly. I don't know. I'm just kind of wondering whether this is people have discovered this is a better way to do it.
It probably just works really well. It's probably just very efficient, and there's no reason to change it. I think the only reason they might ever need to change that stuff potentially in the future is they've made certain assumptions with Fortran that things are going to be a certain size, and that kind of limits the size of data frames and things like that you can have in R. So if that stuff is ever overhauled, they'll probably they might move to something else. But if you look what actually goes on in R when you do simple stuff like matrix calculations and all that kind of stuff, it calls out to Fortran, quite often, probably a lot more than you think. So, yeah.
My question